I'm Paul Den Hout, demonstrator extraordinary in physical metallurgy. In the Sharpie test, we evaluated how brittle or ductile materials were by subjecting them to impact. What we'll be doing now is subjecting test pieces to tension. In other words, a tensile force. So that's a force that pulls apart. As with the Sharpie test, we had to have test pieces, and the test pieces that we have for the tensile testing is effectively a dog bone. And once again, it's made to very tight specifications. It has a cylindrical cross-section, a diameter of 7 millimeters, and an internal length of 37 millimeters. And the apparatus we use is what you see on the right here, the tensile testing machine. We'll be looking at 4 different materials: copper, mild steel, brass, and aluminium. So the dog bones are made to identical specifications. The apparatus secures the test piece, and this arm, by lifting, subjects the test piece to tension. So the first thing we need to do is to mount it. What we have are grips, and you'll notice that there's a lip on the grip, and that lip holds the test piece in place. There's a pin and a ring. We secure it by placing the 2 hemispheres together, slipping the ring over the 2 grips, and then the pin, which will run through one end of the apparatus. The bottom secured, and we do likewise for the top. All right, so we do the same then. There we are, we've got it in, and then we push the clamp up. So the test piece is now secured between the 2 legs of the apparatus, and we're set to go. So the apparatus is connected to software that records all the information that is needed to evaluate the particular property. So what we're really after is the force that's being applied, the tension, and the strain, which is the deformation that the material undergoes. We have now zeroed, and we're now ready to go. With our test piece in position, we can now record what information we need to on the computer. And the 2 bits are the diameter of the cylindrical core and the length of that core. So that's 7 millimeters and 37 millimeters. So that information is keyed in over there. We can zero, which is already done. And when I press start, it should go. And now you see it. It's elongating, and the force is increasing. So it's climbing, climbing. Now it's leveling off. So it's elongating, it's going into plastic deformation. Tensile force applied is not increasing. As it deforms, it gets longer and longer. It's now stretched by over 2 millimeters, 3 millimeters. And now the tensile force is beginning to decrease, the stress in other words, and we're approaching the point at which it will fail. Elongation is at 6 millimeters, stress is decreasing. All right, and there it's dropped. And it's actually failed, but without any sound. And you can see now how it's elongated, narrow, and has actually fractured. Once we've collected the information, we can now dismantle the test piece. We're ready now to set up for the next test. And this time we'll look at the mild steel specimen. And now we mount it. So we mount it in the same fashion as before. All right, I've just adjusted the tension so that when it starts immediately. There isn't a period where the instrument is pulling apart, but it's not applying any stress on the test piece. And there you see it. It's now going through plastic deformation. It stopped, but it didn't snap. It started failing. It's given 1 point, so it's done. That's all there is I can do for this one. So we can put on the other ones and let's see what happens. It should have snapped, but it went right down. It's actually deformed plastically inside, but it hasn't actually broken. The computer's collected the information. We can now dismantle the test piece. Right, this is the brass specimen that we're testing. There she goes. Okay, it's going to go now. You can now see the fracture surface. So fairly brittle in that there's not much elongation. You don't see it narrowing. The diameter is roughly the same as the initial diameter, 7 millimeters. But one could look further with a microscope at that fracture surface and see exactly what happened. Right, we're ready now to set up for the next test. And this time we'll look at the mild steel specimen. So its specifications, dog bone is identical to the copper one that we had a look at. The information's been entered on the computer. We're ready to go. Start. Right, it's now beginning to go through plastic deformation. So the tensile force is leveling off and it's elongating. It's beginning to drop now, the tensile force. And it snapped. And you can see that the tensile force started dropping off and then fractured. So if we have a look now, you'll notice that elongation has now made the cross-sectional area somewhat smaller before it finally fractured. Right, the last specimen to be tested is aluminium. So you see the elastic deformation. Right, it's leveling off now, so it's into plastic. When all the samples have been tested, we should have 8 pieces looking like this. Then we're ready for the last bit, which is part of it is to collect the data on the computer. So that will give us stress-strain relationship, and the strain relationship shows the extent of elongation. The last 2 things that you will need to do is to measure the change in the diameter. 7 millimeters has shrunk to something that's a little smaller. What you do then is to measure the diameter of that face that you see, and for that we use a vernier caliper. Now the vernier caliper has teeth, if you like, that allow you to measure the diameter. If you're measuring external diameter, you would use the lower one. If you're measuring an internal diameter, you would use the top 2 teeth. The scale is in millimeters, and what distinguishes a vernier caliper from other scales is that it also has a scale from 0 to 10 that allows you to measure fractions of a millimeter. You would set it up to measure that diameter, and then you would read. First, on the millimeter scale, that would tell you in millimeters, and then in a fraction of a millimeter, you would look at the lower scale. To read off what that value is, you look for the lines that are aligned, the lower one and the gradation marks on the millimeter scale. And that allows you to read it to 1/10 of a millimeter. So that's what you would do for all your test pieces. And the last thing that you would then do is to examine that surface, the fracture surface. And that would tell you something about the brittle or ductile fracturing that took place and what happened to the material when it failed. And that concludes the practical.